All right, pre-cal 12, let's get after it. Here we go, video 17. And we are looking at graphing and solving radicals. So last video, we looked at radicals, domains of radicals, and different properties of graphing them with respect to transformations. Now this time we're going to look at graphing them again, but graphing them for solutions. Solutions are essentially our X-intercepts. So sometimes they'll be easy to determine graphically, other times algebraically is going to be your go-to point, but we're going to look at both in a few scenarios. So here we go. Before we jump into graphing and solving, we need to first remember and identify that there are domain restrictions for radical equations. So what our restrictions are is whatever is underneath my radical cannot be negative, right? We can't have a negative value underneath our radical. So we're going to get an inequality version of our domain. We're going to get a range of potential solutions. So all we have to do is solve a basic grade 9 inequality statement. Whatever's underneath my radical here has to be greater than or equal to 0. And then we solve that. So add 3 to both sides, and then divide both sides by 2. So that is a domain restriction on our equation. So x has to be greater than or equal to 3 over 2, which means graphically it only exists to the right of 1.5. And that is going to be really helpful when we go to graph things, when we want to test range points, so on and so forth, because we have a starting point. And oftentimes that'll either be our lowest point of the graph as well, or our highest point of the graph, depending on whether or not we have a reflection in the x-axis. Now let's look at this one, because this one here, we have two things to consider. We have a radical statement here, but then we also have a radical statement here. And the thing is we need to satisfy both of them. So let's do these one at a time. 3x plus 4 has to be greater than or equal to 0, which gives us 3x has to be greater than or equal to negative 4. So x has to be greater than or equal to negative 4 over 3. And if you consider that on a number line, okay, here's negative 4 over 3. We can be equal to it, but we have to be greater. So that any values that come up, right? So, here's 0, here's 2, here's 4. Any values that come up and are covered by that line are potential solutions for that chunk of the domain. But we need to check both. We also have 2x minus 4 has to be greater than or equal to 0, which gives us 2x has to be greater than or equal to 4, then x has to be greater than or equal to 2. So therein lies a bit of an issue, because now we have another chunk that gives us this. And we need to satisfy both. So our domain restriction doesn't actually start until we satisfy both. So only those values of my white line actually matter, because only those values of my white line are also covered by my yellow line. So in this case, we would reject that domain restriction. It doesn't actually do enough for us, and we would take this one, because that one covers both of our scenarios. So you got to be aware of that sometimes. You can have values that cover in between sections as well. And you may see that in some of your examples moving forward. What I mean by that is, let's say you had a number line here, and say that was negative 3 and that was positive 3, and say you had a domain restriction like we've kind of seen before. X has to be greater than or equal to negative 3, but x has to be less than or equal to 3. Well, that means you have one line that goes that way, and you have one line that goes that way. So the only line that we take is what is in between both, right? We can't take the outer ends of it. So that's an example of intersecting domains. Okay, so now let's get to solving these things graphically. Now we're going to look at a few aspects of our graph, particularly our domain, sometimes our range, you'll see our y-intercept, and then we're going to do a table of values to solve for some other points. So let's first look at my domain. My domain restriction is 5 minus x underneath. So I need to solve for 5 minus x greater than or equal to 0. So 5 is greater than or equal to x. So there's my domain restriction. We can flip the script there and say x is less than or equal to 5 if you prefer to look at it that way. Now, if you test your low point of your domain, you'll often find the low point of your range, but not in every case. So let's do that here. If x is equal to 5, then we have 0 underneath our radical, and we have minus 2. Then y is minus 2. So it's very possible that minus 2 is the low end of my range, because we're only going to increase, right? This is an increasing graph. It doesn't have a negative in front of it. So let's leave it like that for now and just kind of see the behavior of our graph as we graph it. And now what's my y-intercept? My y-intercept occurs when x is 0. So I have the square root of 5 minus 0 minus 2. So the square root of 5 minus 2, which is approximately 0.24. So my y-intercept is about 0 and a quarter, we'll say. Okay, so where do we have a point on my graph? Well, we already know we have a point right about there. Where else do we have a point on our graph? Well, we know we have our point at 5 comma negative 2. And that potentially might be the low point of our graph. So now we just need to check in between. Now, if you think about this, actually that will definitely be the low point of our graph, because our graph, there's no negative value up front, so we're opening upwards, right? So our general radical, I'm just going to draw a pretend one up here. Remember, our general radical mother graph would have a behavior that looks like that. So we're going to have a similar behavior here. We just have, again, we're going back to transformations. If we were to transform this radical, we pull the negative out and we have x minus 5. So you can see you have a reflection in your y-axis, which is why our graphs look in the other direction. So you can see that, and we've dropped, here we go, and here's our vertical translation down 2. So you can see that we've dropped down 2 and we've reflected in the y-axis. So yes, our graph is going to come up. So that is definitely our range point, right? That's our low end of our range as well. You'll see on the next example what I mean by that. So now let's just pick a few other points, throw them in our table of values, plot them out, and see what we end up with. We have 5 and negative 2. And we have, let's pick something else. And when you're picking points, I get in this conversation all the time with students are like, well, what points should I pick underneath? Well, it's helpful to pick points that are that give you perfect squares underneath the radical. And if you think about your perfect squares, you have 1, 4, 9, right? Those are generally your first few. So what value of x will give me a perfect square under there? Well, if I put 1 in for x, if x equals 1, I'll have 5 minus 1 is 4. So then I'll have root 4 minus 2, which is great. And when you look at that, I get 0. So when x is 1, I get 0. And then another value to put in there, if I pick x equals negative 4, because you can see in your graph we're kind of heading that direction, you're going to get root 9. And I picked those values because I can root both those numbers. Minus 2, so 3 minus 2, and I get 1. So we have a point at negative 4 comma 1. It's just easier to pick points that you can see are going to cross. So, okay, where does this go on my graph? Well, negative 4 comma 1 goes right there, and 1 comma 0 goes right there. Now, looking at that, what we're looking for is we're looking for solutions, right? And we can see that we have a solution here at 1 comma 0. But it's always helpful when we solve algebraically that we're going to need to test that point. Now, we don't need to test the point here because we solved by plugging it right in anyways, so we know it's going to work in our equation. So that's the graph of that function, and that is the solution is staring you right in the face. We found that it crosses at 1 comma 0. So what does it mean then, instead of solving it by graphing, to solve it algebraically? Well, to solve it algebraically, we are isolating x when y equals 0. So remember again, we have our domain restriction. It's the same domain restriction. So x has to be less than or equal to 5. And then we're going to solve algebraically. So f of x becomes y. So we have this statement here. We did a lot of this in grade 11, so we're just going to do a little bit more here. We set y equal to 0 because that's what we want. We want our x-intercept. And now you want to isolate your radical symbols. So I'm going to add 2 to both sides. Because now once you have that, if you square the radical, it cancels with the square. And that's perfect. If we had other values over there, we'd have to FOIL, we'd have to do some crazy things. Then we square both sides. And we get 4 equals 5 minus x. And then we're going to isolate x. So negative 1 equals x, which means, or equals negative x, which means x equals 1. So same solution we got on the graphing page, but when we solve it algebraically, we need to check for extraneous solutions, because when you square both sides, you create potential solutions that work algebraically but don't work functionally, good word choice there, in the function. So we just need to test it, okay? So we say, okay, let x equal 1. Well, that means that 5 minus 1 minus 2 should be 0. Well, that's root 4. Oh, we're looking pretty good. Yes, 0 equals 0. So we can be sure that's true, so that's true. So we have a solution. It is not an extraneous solution, and it also satisfies our domain restriction. It is less than or equal to 5. So that is your algebraic solution. Algebraic solutions can oftentimes be much easier to find because it's possible that our graphical solutions do not cross perfectly at a nice whole number intersection. But for the ones we have chosen here today, you'll see that they should all work both because we want to highlight both aspects. So let's look at a different one here. Now in this case, we have x plus 6 and then minus x. So this graph is difficult to consider with respect to transformations because this is the first time we've seen in a transformation our x occur multiple times in the equation. So you can't really look at this and just say, okay, I'm shifting 6 to the left and then what, right? That x is a bit of a unknown with respect to transformations. So let's still start by identifying our domain. We have to make sure that x plus 6, what is underneath my radical, is greater than 0, which means x has to be greater than or equal to negative 6. So our domain, x is greater than or equal to negative 6. Now, if you plug negative 6 in for your domain, obviously you're going to have 0 underneath your radical, then minus negative 6 gives you positive 6. So potentially our range is going to be something positive 6, right? Because when x is negative 6, y is going to be 6. So we know we have a point right about here. So the question is, though, what does the graph look like after this? So from there, what we'll do is let's solve our y-intercept first. We'll set x equal to 0. And if x is 0, what do we get? We just get the square root of 6 because we have a 0 here and we have a 0 here, right? And the square root of 6 is about 2.45. So we have a y-intercept right about there. So you can see your graph is tending downwards. But the one thing we can see with transformations is if there's no negative sign there. So our y values haven't switched. We're not opening downwards. So this graph is going to still maintain that kind of up scenario, except it's going to shoot down. So if you were to plug this into Desmos, you would notice that this kind of goes up and then fires downwards. So that's why your range here is difficult to calculate, because this is not going to be your range value. So what you'll do is you'll leave this blank, and once your graph is finished, you'll plug the equation into Desmos and you'll get your range value. You'll just have to find the peak of that range, and it's slightly over 6. It's not the end of the world. The range isn't the most important aspect of this question, but just be aware that that is possible. So now let's pick some x values just to continue solving through, satisfy some more of this table of values. And remember that we want to pick points underneath for x that make underneath our radical perfect squares. So what are our perfect squares? Well, 0, but we already have that covered because when x is negative 6, we have 0 under there. The next one would be positive 4. So we could say let x be negative 2. Because if x is negative 2, we get 4 and then minus negative 2. So we get 2 minus negative 2, we get 4. So when x is when x is negative 2, we get 4. So we have another point on our graph right there. And then you can see we're trending towards our y-intercept. So that's good. So now my next perfect square after 4 would be 1. So let's say let x equal, go back to white here, let x equal negative 5. Well, when x is negative 5, we have 1 minus negative 5. So what do we get here? We get 6. So we get 1 minus negative 5, and we get 6. But now we see that again right about here, right? And here's where you should be like, okay, hang tight. Wait a minute. How can we be at 6 again? And that's why you know your range is different, because it's gone up slightly and then it shoots back down through 6 twice, right? So that is why the range is difficult to calculate. So now let's continue down this direction, but let's think, okay, I'm heading towards my x-intercept. So let's pick a value for x that is in the positive realm. So what's an x value that's positive there that will give me a perfect square? Well, if I have 9 underneath my radical, I'm going to have a perfect square. So why don't we let x equal 3? And that way I now have root 9 minus 3, which is 3 minus 3. Oh, would you look at that? I now get my x-intercept at 3, 0. So this graph is going to continue down like that, and you have your solution right here at 3, 0. Now, if you were being asked to find the solution to this and given access to Desmos, you could just plug it in, and you're looking, when it says find the solution, remember you're looking for the x-intercept. So there it is, we found it in this one. And again, the range can be tricky sometimes because, as you can see, this one kind of comes up and then goes back down. So your range is this small peak right in between. So it'd be slightly over 6. You could say, if you really wanted to, you could say your range is strictly less than 6.5, because it means it's less than 6.5, but still a ballpark, okay? So that would be an estimate. You would want to use a graphing app, or eventually you'll learn in calculus how you can get the exact value there, but we're not going to go dive too deep into that right now. So let's look at this algebraically then, because this one's a little bit different than the previous question. We have to do a little bit more work because we have 2 x's in it. Again, we have the same domain. X has to be greater than or equal to -6, so we have to satisfy that. But now we set f of x equal to 0, and we're solving this. Now again, you still want to isolate your radicals. So we're going to add x to both sides. That kind of gives us this here. Now we're going to square both sides, and we get x squared equals x plus 6. And now you can see we have the beginnings of a quadratic. So we're going to subtract x and subtract 6 from both sides of the equation, and we get x squared minus x minus 6 equals 0. And that factors out to x minus 3, x plus 2. So we have 2 solutions, right? We got x equals 3, and we got x equals -2. Now we just found graphically that only one of those worked. When x equals -2, it didn't make sense. And that is why we need to check these solutions in our original equation. Now, first thing, yes, they both satisfy our domain, so we can't reject them for that sense. But what we have to do is we have to chuck them into our original equation. Now, this one we already did because we did it when we solved graphically. But here we get a good scenario. We get 0. But you'll notice here, if we throw root -2 in there for x, we're going to get root 4 minus -2, which gives us 2 plus 2, which gives us 4. So that's not true at all. That doesn't equal 0. So we reject that answer. That is what we call an extraneous solution. We don't keep it, so the only solution to the equation that we keep is x equals 3. So let's look at another one. So here we have yet another challenging question. So what is our domain restriction? Well, 4x plus 1 has to be greater than or equal to 0. So 4x has to be greater than or equal to -1. So x has to be greater than or equal to -1/4. So we have -1/4 is our domain restriction. And if we plug that in, we're going to get -2 as a result. So that means we have a point at about there. And transformationally, we don't have any other x values, so that's going to open up. And you know that it isn't going to do anything else funky otherwise, so you can also say that you now have your range. So x is greater than or equal to -1/4, and range y is greater than or equal to -2. So we can identify both of those things. And then our x-intercept occurs when x is 0, so we would end up with 0 in here, so root 1 minus 2. So 1 minus 2, we would get -1. So we get our y-intercept at 0, -1. So we can throw that into our table of values as well. So you can see we're opening up this way. So we're going this way. Now the thing is we want to find our x-intercept. Now this is where graphically it can become a challenge, because ideally we want to pick values for x that will give us perfect squares underneath. And what will do that? Well, perfect squares would be 4, which we have already. We know we're opening that direction, right? So if we pick x equals 1, we're already going to be too big. If we pick x equals 0, well, we get our y-intercept. If we pick x equals anything negative, well, we're outside of our domain. So what we need to do is we need to pick the next possible value, which would mean this is 8, because 8 plus 1 is 9. So we'll say, okay, well, what if x is 8 then? Because it's hard to sort of pick in between there and find perfect squares. But we'll find a couple more. Sorry, not x is 8, x is 2, right? Because that'll give us 8. So if x is 2, we get 8 underneath there, so we get 9 underneath the full radical, so we get 1 as our solution. So when x is 2, we're at 1. So you can see we've already crossed through the x-axis. So our solution here is difficult to find graphically. So you can find a ballpark solution here. It looks to be slightly less than 1, but it's not really easy for us to calculate graphically. So this would be a scenario where, okay, you know what, we're going to have to default to algebraically and then go back from there. So what we'll do is we'll solve this algebraically and then we'll compare our answer to our graphical answer here. So we still have our same domain, x has to be greater than or equal to -1/4, and now we will solve this algebraically. So 0 equals the square root of 4x plus 1 minus 2. We're going to add 2 to both sides. And then we're going to square both sides. And now we get this statement here. Now we're going to subtract 1 from both sides. We get 3 equals 4x. Would you look at that? X equals 3 over 4, which is 0.75. So just slightly before 1. Now we would want to key that into our equation to make sure it makes sense. Right, we have 4 times 3 over 4 plus 1 minus 2 should be equal to 0. Well, that means 0 is equal to 3 plus 1 under the radical minus 2 because the 4's cancel there. So 0 equals root 4 minus 2. 0 equals 2 minus 2. Yay, 0 equals 0. So that is in fact a root. And if we go back to our graph, we can say that that is, 0.75, 0. Again, not easy to discern graphically always, which is why graphically can be helpful when you get those perfect solutions, but when you don't, algebraically is going to be a much more of a guarantee when it comes to determining our roots. So I think we're going to do one more here, and what we'll do with one more is it's going to be a fully loaded graph question, but then definitely a fully loaded algebraic question. So you can see right away, this is going to be one with a difficult to calculate range once again, because it's not a traditional function notation. We don't only have the x under our radical, so we can't make any sort of inferences with respect to our transformations. So what we'll do is we'll start by solving our domain restriction, and then we'll leave the range for a little bit, and we'll come back to the range. So for our domain, x plus 1 has to be greater than or equal to 0, so x has to be greater than or equal to -1. So we know that right off the bat. And when x is -1, what do we get then, right? Because that's our leftmost point on our graph. So when x is -1, we get 0, and then minus -1, we get 4. So, or sorry, that's a 2. We get 3. So when x is -1, we get 3. So we can throw that in. When x is -1, we get 3. So we have a point here right there. Now, what about our Y-intercept? Let's calculate our Y-intercept. Our Y-intercept occurs when x is 0. So when x is 0, we actually get the square root of 0 plus 1 minus 0 plus 2. Well, that's just 1 plus 2 again, which again is 3. So interesting. Here we have a scenario where we have the same y value twice again, which means not really sure what my graph's going to look like from here, but I know it's tailing off to the right. So let's pick another point and see where we end up. So let's pick a point so that we still have a perfect square underneath our radical. So the next perfect square that I would search for here would be 4, which means let's let x equal 3. Because then what we get is we get 3 plus 1 minus 3 plus 2 is root 4 minus 1, which is 2 minus 1, which gives us 1. So when x is 3, y is 1. So now we're down here, 1, 2, 3. So you can see your graph heads that way. So obviously, if you have the same y value there and there, our graph's going to go up slightly again, right? It's going to kind of bow up, but then it's going to cut back down. And that's why your range is difficult to discern in these scenarios. This would be one where if you really needed the range, you could Desmos it, or again, when you get to calculus, you'll learn a fancy way of figuring it out. So now you can see we're heading towards our X-intercept. So let's take the next perfect square after 4, which would be 9. So if it's 9, so if we want 9 underneath here, that means we're solving x equals 8. I'll just throw this back in here. And we'll do that. And we'll do that. Okay, so if x is 8, that means we have root 9 minus 8 plus 2. So we have 3 minus 8 plus 2, which is going to give us negative 3. So when we get 8, we're at negative 3. So again, when we cross this now, 6, 7, 8, down here 3, see we're trending downwards. And graphically, it's difficult to say where that crosses. So graphically, difficult. So let's jump to algebraic. Let's solve it algebraically, and then we can come back to our graph. So algebraically in this case, we now have still the same domain. But you can see in this scenario, it's the first time we've had multiple terms that are not underneath a radical. The one time we had 1x, and that was fine to deal with, but this time we don't. But we still want to isolate our radicals, so we're going to add x to both sides and subtract 2 from both sides. But what that does is it gives us a statement like this. And here's where we often come up with main algebraic pitfall number 1. When you square both sides here, you cannot just square those things. That is a super no-no, big time not allowed. Don't you dare ever do that, because this is a statement now. So if you're squaring both sides, you are squaring and you are squaring. And this means FOIL. That is where one of the biggest errors occurs in solving radicals. So what we end up getting is we end up getting x squared minus 2x plus 4 equals x plus 1. And then we isolate to set equal to 0, and now we get x squared minus 4x plus 4, and then minus x minus 1 equals 0. So x squared minus 5x plus 3 equals 0. And now in this case, we end up with a quadratic that is a little nasty, cannot be factored easily, so we just need to use our quadratic equation. And remember that that's negative b plus or minus the square root of b squared minus 4ac all over 2a. So we end up with 5 plus or minus the square root of negative 5 squared, which is 25, minus 4 times 1 times 3, all divided by 2 times 1. So 5 plus or minus the square root of 25 minus 12 all over 2. So 5 plus or minus root 13 over 2. Not an ideal looking number, but a number nonetheless. Now when we plug that in, we get two solutions. We get 0.697 and we get 4.303. Now if we go back to graphically, 0.697 is like right here. So you can imagine that there's no way that's true. So if you plugged that into your equation, you're going to find that this comes back as an extraneous solution. That's why pairing things up graphically and algebraically are helpful. And if you plug this in, it's going to work, and you'll notice it should work because look at our graph, it crosses just after 4 and in between 5. So that's our 4.303 solution. So we can tie the two things together and we're good to go. So graphing radicals can be a little bit challenging. Certain behaviors, depending on the complexity of the radical statement, make your radicals shape vary more than you're used to. But it's all about identifying some of those key points and remembering that it's going to be a smooth graph from there. Definitely start by isolating your domain and your range, and then pair it up algebraically to try to make sense of potential solutions. So that is our section on radicals. Next, we're going to look at rational statements, which are our good old-fashioned functions with denominators. So we get to make a lovely visit into the world of asymptotes once again. All right, thanks so much, and I'll see you next time.